Must be between 0 and 1. 1 means perfect efficiency. 0 means it's worthless. This efficiency is defined as the ratio between the power that the antenna actually radiates and the power that you give to the antenna. And obviously, being the power that you give to the antenna greater or equal to the power radiated, this number is between 0 and 1. So how do you put this into the equation? In this equation, it is simple because you just replace the transmitting power with theta times P. And P is the power to the antenna. Now, this parameter here, product of the directivity times efficiency is what we call antenna gain, la ganancia dell'antenna. And this is what you find on the specification of your antennas. And depending on the efficiency, the gain of the antenna can be quite low. In particular, when the antenna efficiency is very low. Okay, the antenna efficiency can be very low if you are buying something that is very cheap. Maybe from China or over eBay, for example. And, but maybe very low, even if you are a good engineer and you are done the very best. Because unfortunately, you may have noticed, antenna, they do not follow the Moore law. That is, they cannot be made smaller and smaller and smaller in divisions. Antennas that are small with respect to the wavelength, not small in general, but small with respect to the wavelength, have a very low efficiency. And there is no way to counteract this. Sometimes you have to be very small antennas with respect to the wavelength, and you have very low gain. But there is nothing you can do about it. There is no magic in this. How do you express the gain usually? The gain is usually expressed in dBi. That is dB with respect to the isotropic radiator. dBs with respect to the isotropic radiator. And since the isotropic radiator D is equal to 1 for the isotropic radiator, the gain is simply K into pi is simply 10 logarithm base 10 of G. And this is a parameter that is more important than the directivity itself, because it takes into account the efficiency of the antenna. Okay, now what else? Let's see now what the antenna looks like from the transmission line point of view, from the generator point of view. Sorry, questions so far? Curiosities, doubts? Is it okay? Am I going at the right speed? Now, we have our antenna. We have the port where the generator is connected, and what these things look like to the generator. What is the equivalent electrical circuit of the antenna from the generator point of view, or from the receiver, or from the transmitter point of view? That is, should we introduce some electrical components here? Which components? Resistor, inductor, capacitor. Which one you will introduce in that model? That's it. That represents the antenna, the behavior of the antenna. Tricky, yeah? Okay, I will help you. The antenna is radiating energy. So the generator is injecting a power P to the antenna, and this power is radiating. What is the only electrical component that can absorb energy? Resistance. Inductor and the capacitors, they do not absorb real power, because the power that they handle is purely imaginary. It's reactive. So this component is a resistance, and is something that describes the radiation. It's not a real resistance. You cannot measure it with a tester, with a multimeter. It's something that appears only when the antenna is radiating. It's something related to the radiation phenomena, and so we call it radiation resistance. Okay, this radiation resistance exists even if the antenna is lossless. But the antennas are not lossless. So some part of this energy, of the energy that the generator is transferring to the antenna, is lost has heat, obviously. Those are ohmic losses within the antenna. So which component describes this power loss, this dissipation due to internal losses? Again, another resistance. The only component that can absorb and dissipate power. This time, this resistance has a completely physical meaning. This is an actual resistance. That is, actually the antenna warms up. It can actually melt down if you put too much power. You can actually burn the antenna and melt it. This is called loss resistance. And then there is something here that you cannot, which is not so easy to imagine, because there is a reactive, maybe a reactive component that is the equivalent or inductor or a capacitance, depending on the way the antenna is built. It's very difficult to calculate analytically those quantities, but luckily there are fantastic simulators that do all the mathematics for us. Okay, so from the generator point of view, this antenna is equivalent to a complex load where this is the total resistance of the antenna. This parameter is what you call the impedance of the antenna. And why it is important? Because you have to connect the antenna to a transmission line or to a generator. It is extremely important that the impedances are matched. In our practical world means that the impedance of the antenna must be the same as the impedance of the transmission line. Usually those values have been standardized. A very typical value is 50 ohm, but you can find also 75 ohm, 150 and 300. Those have been standard values because the people that is building the transmission line, people that is building the coaxial cable, etc., they work with very precise impedance values. They cannot build any arbitrary value. They could build any arbitrary value, but it would be extremely expensive. In your career, I think that 99 or 99 maybe not, but 95% of the time you will find 50 ohm as a standard impedance for antennas. 75 in some cases. What happens if the impedance are not the same? there is, in the best case, there is a mismatch, so some of the power from the transmitter bounce back to the transmitter. So the radiated power is even lower. In worst case, you can damage the transmitter, but that's another story. Usually you work with matched impedance. 50 ohm. Oh, now you can imagine that there must be a precise relation between those two resistances and the antenna efficiency. And that's the case. Now imagine that there is a current E circulating into the circuit. What is the radiated power? The radiated power depends only on the radiation resistance, because the radiation resistance is responsible for radiation. Lost power depends only on the loss resistance. Now, total power, the total power that our generator is transferring to the antenna is the sum of the two powers. It is if you collect RT squared is and please remember the definition of efficiency, that is the radiated power divided by the total power. So if you replace into this equation and you find out that the current you see that the antenna efficiency is related immediately and very simply to the radiation resistance and the loss resistance and their relative ratio. And this is some other equation that we will use when we do our exercises. So far we have been talking about transmitting antennas, but what happens when the antenna is receiving? The same antenna is received. What happens? Before we tackle this, there are questions so far? Okay, in principle, okay, we should we should not take things for granted, but it can be demonstrated. We don't do it because it is very boring. already demonstrated that. It's not video, but so you can believe. The directivity function does not change. When the antenna is receiving instead of transmitting, it can be demonstrated that the directivity function is the same. That is, the antenna receives best where in the direction where it transmits best. It's not obvious. And then the polarization of the antenna is the same. That is, it receives a wave that has got the same polarization of the wave that the antenna will transmit. So if the antenna transmits vertical polarization, it is the best performance are when the incoming field is vertically polarized. Same polarization. Having said that, what are the parameters of the receiving antenna? So, this time the antenna is working on the other way around. That is, somewhere a transmitting antenna that is out of this blackboard is generating an electromagnetic wave. This electromagnetic wave is incident on our receiving antenna. And the antenna is doing the opposite conversion. It's transferring a power, the received power here, to the receiver. Now, let's assume that the polarization is the same. The polarization of the incident wave is the same. What is the receiving power? Obviously, it will be a function of the incident power, because if there is no incident power, there is no receiving power, times a coefficient. We don't know much yet about this coefficient. But we know something, for example, what are the dimensions of the receiving power? What is the dimensionally, what are the dimensions? But the incident power, we saw it yesterday, is a power density, so it's watt divided square meters. So if the things must be correct, what are the dimensions of this parameter? Square meters. So this is what we call effective area of the antenna. Or capture area. But capture area is an old definition. The modern definition is effective area. Please note that the effective area, this is important, the effective area has nothing, in principle, has nothing to do with the geometrical area of the antenna. Okay? Unless very, very specific cases, the effective area is something that is not related to the geometrical area of the antenna. It's an electromagnetic parameter. It's not a geometrical line. Now, there is one another thing that can be demonstrated, we will not demonstrate it, that for any antenna, however you build it, whichever shape, material, or you use to make it, there is a universal relation that holds always. Gain divided by effective area that's a universal relation, and we will use that relation to go from effective area to gain and vice versa. I am not demonstrating it. Take it for granted. Okay, so what happens is that if you look through a catalog of an antenna producer, you will never find the effective area. It will never show. They will never give you the effective area because they give you the gain. So once you have the gain, you have the effective area. Okay. And we will use more often the gain than the effective area. Okay, so another thing that can be demonstrated is that the impedance of the antenna does not change when you use the antenna section. So, if we want to construct an electrical model of the receiving antenna, radiation resistance, loss resistances, reactance, if any. And now we're missing something here. What are we missing in this one? What are we missing in this model with respect to that? What is the antenna doing now? It's transferring some power to the receiver. So what is missing there? A generator. A voltage generator. Where does this voltage generator take its energy from? The incoming electromagnetic field. So this voltage generator must be linked to the electric field of the incident wave. Let's use this for E0. Time parameter that we will discuss in a moment. So, voltage generator dimensions are volts. What are the dimensions of the electric field? Volts per meter. So this parameter must have dimensions of meter. This is called effective length of the antenna. Again, the effective length in principle has nothing to do with the physical length of the antenna. It can be related, but in a quite complicated way. And one other thing, the effective length can be a complex number, not a real number. What does it mean? Remember that all the quantities we are talking about are phasors. Fields, currents, voltages, all phasors. So, if the length is a complex number, what does it mean? It means simply that the voltage is not in phase with the electric field. Nothing special. So don't worry if the electrical length is a complex number. It just means that there is a difference in phase between the electric field and the voltage. Okay, so this generator is transferring a power PR to the receiver. What is the power that can be transferred to a load? If you have done some, if you have seen some circuit theory, you know that the maximum power that can be transferred to a load is called the available power of the generator. Maximum power that you can transfer to a load, this maximum transfer happens when the load is matched to the generator. It is when ZL is equal to the complex conjugate of the antenna impedance. And since usually the antenna impedance is real, so there is no imaginary part, there is no problem with the complex conjugate, it means same impedance of the antenna. This is the best you can do. The maximum energy that you can transfer. What is the value? It can be demonstrated, maybe you know that in this situation, the power to the load is the so-called available power, and is equal to let's say the maximum power that you can transfer your load. This is also the receiving power. And we will see in a moment that this quantity is directly linked to the effective area multiplied. We had another expression of receiving power, was written there before, and the two things must be the same. And we shall compare those two and find out the relation between the effective area, the effective antenna length, and the impedance after the break. Questions?
Yo sí, voy a pedir una explicación.
The more you concentrate the energy in the direction, the higher